Good morning, good afternoon, good evening, wherever you are in the globe, and welcome to today's webinar. We are delighted to have such a distinguished guest and audience as we are exploring architecture and design innovations. We appreciate your presence and look forward to sharing insights and discussion that will inspire and inform our own work. My name is Nabil Muharib, and I am an associate professor at the American University in Cairo, Department of Architecture. And with me, Assistant Professor Rania Khalil and our RA, Mariam Magid. And of course, we have our distinguished guest, Wassim Jabi. So if you allow me, I'm going to share a few slides, and then we're going to start directly with our guest. First of all, who we are. We are a new community. We're calling ourselves Spatial Analysis and Simulation Community, having like some sort of a capacity building for postgraduate students and early stage researchers. So we are excited to launch our free volunteer-driven research community, focusing on urban simulation and spatial configuration, and of course, architectural analysis. Our key activities include capacity building, like an online webinars and a regular online meeting with postgraduate students for discussion, and some sort of like one-on-one workshops on urban simulation methods and environmental analysis. We are seeking collaboration, trying to find some sort of collaboration research, joint research projects led by senior researchers and opportunities for junior researchers to participate. So in total, we are aimed to foster collaboration, provide mentorship and advise innovative research in our field to create a supportive environment for learning, applying and developing urban simulation tools to improve the built environment. So we're going to have some sort of regular meetings and workshops, and I'm going to announce all of these soon. So join us in this collaborative journey to push the boundaries of urban simulation and spatial configuration research. And of course, we are delighted and honored to have our own first guest in our webinar, Professor Wassim Jabi. And the title is really interesting, and we're discussing the title just a few minutes before our meeting. It's called Typological Pi, a scientific approach to geometry, topology, and semantics. And of course, I'm going to leave the floor to Professor Wassim, but let me just explore with you biography about Professor Wassim. Is the course director of the Master of Science Computational Methods in Architecture program at Cardiff University's Welsh School of Architecture, United Kingdom. He holds a Master of Architecture and PhD from University of Michigan and has an extensive teaching background in the US and the UK. Professor Jabi has secured significant funding, including a huge amount of grants, almost 250,000 grant and 300,000 grant. And his research encompasses parametric design, building performance simulation, and robotic fabrication. And he's the author of a parametric design for architecture. And please go and visit his website for a topological software library for a spatial topology. It's called Topologic Application. And this is some sort of like screenshots from his work. And actually, I was playing a little bit, trying to search Professor Wassim work or research publications. And as you can see, it's you have a lot of a huge path of research. You can find it. Things started, I don't know, maybe earlier than this, but the 1995 up till today, and the relationship between different authors and between different publications. And of course, we are happy to have him with us. And thanks, Professor Wassim, for your accepting our invitation. And the floor is yours.
Always, Nabil. Thank you so much for the invite to this new group and for the kind words that you have started this presentation with. And thank you all for attending this talk. I hope you will find it interesting. So I'm gonna just jump in immediately and share my screen. Just to expand a little bit on the introduction. Yes, my name is Wassim Jabi. I am a professor of computational methods in architecture at the Welsh School of Architecture in Cardiff University. I taught in the US for a long time, and then we moved to the United Kingdom in 2008 to the Welsh School, and I've been at the Welsh School now for about 16 or 17 years, actually. And at the Welsh School was really a good home for me because it allowed me to develop my research interests, and they supported me quite well. And I developed kind of three different strands of my research. I developed an interest in how to help designers. This is kind of like my core kind of skills and my core research interest from the University of Michigan, where I was part of the group which is called Design Process and Methods. And it came all the way, you can trace its origins all the way back to the 60s, actually, where the kind of formal design processes was a big thing. And Michigan was known for that. But when I moved to the Wells School of Architecture, I found that they are really strong in building technology. And if you know the piece of software called Ecotect was developed at the Wells School of Architecture, actually, before it was purchased by Autodesk. So I wanted to combine then my work, how to help designers, kind of creating computer-aided design tools, parametric design tools, with building simulation and kind of trying to help that area. At the same time, I was also interested in how we translate our designs into physical products and physical buildings. So I was looking at digital fabrication. Obviously, that was a very big thing. And in 2013, I convinced my school and the university to fund me for about £70,000 to purchase a large KUKA robot, 2 meters, and to do some kind of 3D printing and CNC work with it. And that has developed quite well. And we have kind of published a few papers on 3D printing of sustainable materials. So we started looking at how do you have designers design sustainable structures? How do we use sustainable materials like cob instead of concrete, instead of 3D printing concrete, which is still harmful for the environment? And then how do you actually digitally fabricate it? So these are kind of like the three things. All of that has kind of given me this idea, and it's a theme that has been in my mind for a long time, that research is not one thing, and we as humans are not about one thing. We're not like a one-liner. We combine different interests, and these interests somehow exist in our mind at the same time, and they help each other. Somehow, like one area feeds into another area, but even though they're desperate areas in the sense they are different areas. So I started searching. When I was working on this new research project that was funded by the Leverhulme back in 2016 and resulted in Topologic Pi, I noticed that Topologic Pi itself is also a combination of multiple ideas that are coming together. So I wanted to find a word that represented that. For those of you who know me, you might know that I am married to a Greek person. So obviously, I wanted to find the Greek origin word that would mean the coming together in one place of different things. And that word that I found was syntopic. So syntopic is a word that you will not find in the Oxford Dictionary or the Merriam-Webster Dictionary, but it is a word used by biologists. And it basically comes from the Greek synchrono or synchronous, or at the same time, or at the same, kind of the word same, and topos. Topos means location, like topography, topos. So syntopic means that things are happening at the same time in the same location altogether. And what biologists use that word for is when different species exist in the same location, and they also help each other because they are existing in the same location. We've all probably seen those pictures of the bird, on the alligator teeth, cleaning their teeth, and the alligator does not eat the bird, or the little birds also on the elephants, they clean their skin, etc. This is a syntopic approach where kind of very different species are existing in the same location, and somehow it works, like somehow it kind of helps each other. So in this talk, I want to talk to you about three things that come together and help each other. And those three things are geometry, topology, and semantics. And I'll explain those terms in more details as we go along. So let's start with geometry. So if I show you this figure, you will tell me, yep, it's a square. It's a geometric object. It's what we call a geometric primitive. It has 4 equal sides. 4 equal corners, 90 degrees. We all know what a square is, and it's pure geometry. It has an area, we can calculate this area, we can calculate its perimeter. Great, so that stands by itself as the kind of initial kind of thought that this is a geometric object. However, if I tell you I would like to fill this square with smaller squares, and those smaller squares belong to two different sets. You can say they are black and white, but black and white becomes semantic. So I'm going to push that a little bit till later. But let's imagine that they are filled with two sets, two different types of squares. And those squares have a certain pattern in which they exist in this bigger square, such that if they are on an index of I to j columns or I to j rows, let's say, if I plus j is even, they are in one set. If I plus j is odd, so you know 2 plus 2 is 4, it's even, it belongs to one color or one set. And if it's 2 and 3, 5 is odd, it belongs to a different color, right? So we can mathematically, formally describe the two sets that exist here. That starts to talk about set theory and what sets mean and how things belong to sets, and also odd and even, so a bit of algebra. But also there is that kind of characteristic of this chessboard is that no two squares that belong to the same set share an edge. So when we start talking about sharing an edge, or something next to something else, like neighbors, right? Somebody above me, somebody below me, somebody to the left, somebody to the right, to the north, to the south. When we're talking about relative positions to each other, we're starting to talk about topology. So you can, a very good example is what Nabil showed at the beginning about the papers that I have published and the other researchers I'm connected to. I am connected to certain researchers that I might have co-authored papers with. I'm not connected to other researchers. And this type of connection is all about topology, how things are connected. It doesn't matter where those nodes were placed on the diagram. They could be anywhere. As long as they're connected, we are still talking about topology. Once you place them in a certain order, now you're adding another layer of information that we will talk about next. So in this case, we can also describe this diagram that we see here as a graph. And the graph, and in this case, to be formal about it, this is called a dual graph. There is a main graph and a dual graph. The main graph is basically all the actual edges and points of intersection of the squares, right? If you just simply look at those edges. The dual graph is another kind of reflection of the representation of this object. In the dual graph, every square is represented by a single vertex, and squares that are next to each other are represented by an edge that connects them. So basically, we get another grid, but it's not the same one. It's kind of like the dual of it, right? But it helps us describe what we are seeing and describe the connections and the relationships that they have. So a graph, formally, G, is made out of V and E. V are the vertices or the nodes, and E are edges, and they are the relationships. Now, if I tell you what you are looking at is not just a square, it's not just black and white squares or just a graph, it's actually a board game. And this board game has a king, has a queen, has a knight, has pawns, has other pieces. And it also has movement rules. And maybe I can tell you these pieces are made out of mahogany wood. These types of things start adding semantics, start adding meanings to you, and that might be different to meanings to somebody else. Maybe there are shared meanings, but these are things that are added as a different layer. So we started with geometry. Obviously, this is a chessboard, as you can imagine. We started with geometry. It's a square. It's 8 by 8. It has topology. It has kind of relationships, but also it has semantics because it's a game of war, and it has a game of strategy and all of that. These are semantics that you are adding to it. So once you have that, it becomes, you open up a whole new world of interpreting and analyzing what happens in this world, in this kind of syntopic world of geometry, topology, and semantics. I'm just going to give an example of one of the things that could happen. That could be an interesting kind of, just a little bit of a game here. Basically, there is something called a Knight's Tour. What is a Knight's Tour? It's basically the path that the knight, which is represented by a horse usually, the way it moves, which is 2 over and 1 over. If you play chess, you would know that, right? So the Knight's Tour is basically a question about this chessboard, which is, if you start at a certain point and you put your knight there, and then you move that knight in the way that the knight should move according to the rules of the chess game, meaning 2 over and 1 over, can this chess piece move all over the chessboard, visiting every node on this chessboard without ever visiting the same node twice or more than twice? Can it do that? And the answer is actually yes, it can. So here is the movement of the knight, and this is the path that it follows is called a Hamiltonian path. The Hamiltonian path and cycles are named after William Rowan Hamilton, but in reality, like everything happens, usually I usually start this talk by saying history is told by the victors, basically, and sometimes the people who win, usually sometimes from Western culture, tell you it's Hamilton that invented it. In fact, it goes all the way back to 9th century in Indian mathematics by Rudrata, and then around the same time in Islamic mathematics by Al-Adli al-Rumi. So nothing usually is what it seems, unfortunately. History is a lot more complex than we make it to be. But basically, what did Rudrata do? Rudrata was not a mathematician, but also he was a poet. And I really like the fact that this kind of mathematical concept of the Hamiltonian path came from poetry, came from a linguistic model. So what was Rudrata trying to do? Rudrata was trying to prove his prowess. He's trying to show off, basically. He was trying to prove his prowess both as a mathematician and as a poet. So what did he do? He basically took a chessboard, and chess obviously goes to 3000 BC, by the way, so the game is very, very old. So he took a chessboard, he took half of the chessboard, so 4 or 8 by 4 squares, right? In those 8 by 4 squares, he filled each square with a syllabus of a poem, of the first verse of a poem that he invented. So you read it like this, and you read a poem. Great. So that's the first verse of it. I can't tell you what the poem is. I don't speak the language. But then using a Knight's Tour, meaning imagine putting a chess piece and moving it along half of that chessboard, along those syllabi, take those syllabi, and then put them on the lower half of the chessboard, he gets a coherent second verse of the poem. He completes the poem. He gets the second verse just by doing the Knight's Tour. And it's quite difficult. I tried it. It's actually, I failed, obviously. I'm not as good as Rudrata by any means of the imagination, but he was proving his prowess both as a linguist and as a mathematician to kind of generate coherent poems or coherent verses of poems by doing a mathematical game, basically. So here is my failed attempt at it. So basically, like everybody else these days, I asked ChatGPT, give me a sentence that is made out of 32 words, 8 by 4. So ChatGPT gave me, the diligent students quickly completed the homework and studied for the upcoming exam, ensuring that they understood all the concepts thoroughly and prepared themselves well for the challenges of the next day. I have no idea why it chose that sentence. I did not tell it to give me anything about students or exams, but it did. Fantastic. So I went and filled those in for half the chessboard. And then I said, okay, let me see if I can do a Knight's Tour and if I can actually make a certain sentence out of it. I only partially succeeded. I found things like the prepared exam challenges all students, and then I couldn't go any further. That's the blue line. If you can kind of follow it, the prepared exam challenges all students. And then another one, the red one, was maybe slightly longer. For quickly ensuring themselves, the exam students studied for the, and then I kind of hit that end. So where am I going with all of this? Is this idea of syntypy, where geometry, I believe that when you combine geometry, topology, and semantics in parametric design systems, in spatial analysis systems, you get more out of the system that you are using. I see a lot of examples where they deal only with geometry, but they ignore topology, or they ignore semantics, or they deal with semantics very much just as attached attributes, but they don't go beyond that. Or sometimes it's missing information. So any kind of system that is supposed to deal with architecture, with spatial analysis, with urban analysis, I believe should address this kind of syntopic approach of integrating geometry, topology, and semantics. Now, we tried to do that. We tried our best, and you can judge for yourselves how well we succeeded or not by inventing this piece of software called Topologic, and now it's called Topologic Pi. So it's based from its name. It's based on the concepts of topology, which I will read here very quickly. Topology delves into the intrinsic nature of spaces, emphasizing that the true depth of our world goes beyond surface level shapes. It reveals the intricate web of connections and boundaries, serving as a reminder that reality is not solely defined by tangible forms, but also by the intricate interplay of relationships between them. With the integration of geometry, topology, and semantics, and artificial intelligence, and we'll talk about that a bit later, we can start the transition from building information models to building intelligence models. And this is what we are hoping to do. When we submitted the Leverhulme Trust that funded the development of Topologic, we basically told the Leverhulme Trust that we would like to reinvent building information modeling. That was our ambition. We do not want to just simply add to it or help it, or we want to really kind of reinvent it from the beginning, because we think it's just gone the wrong way. And I'll try to explain that a little bit. So Topologic Pi is now, unfortunately, everybody has to say AI powered. So it is an AI powered. It does have good AI credentials in it at this point. So we are fine to say that. But basically, what is really important about Topologic Pi is that it is an open source and free Python 3 spatial modeling and analysis software that revolutionizes the way you design architectural spaces, buildings, and artifacts. Topologic Pi's advanced features enable you to create hierarchical and topological information-rich 3D representations that offer flexibility and control in your design process. In short, Topologic Pi enriches building information models with building intelligence. So what you are seeing on the right side is some of the visualizations, and I'll enlarge them in the next few slides to kind of give you a taste of what it does. Basically, Topologic Pi in its DNA knows what is next to what, and that gives you a lot of power. Just that simple idea of when you create an object, it knows its neighbors, gives it a lot of power, and we'll see how that kind of develops. So if you see in this representation, I'm not going to read the text here, but you can take a look at this building. First of all, I'm saying it's a building, right? I'm assuming it's a building. It is a simplified geometry of a building. It's not an actual, like, fully detailed building. And we make a big kind of note about we don't need very sophisticated, very detailed geometry. We need actually to capture design intent. And design intent is about what are you setting out? What is kind of almost like a Vitruvian setting out of a plan? What are the axes? What are the symmetries? What are the kind of subdivision of space? And for that, we don't need doorknobs, door handles, and all the details. We need to understand our design kind of basic partie, basically. So what you see here is a simplified geometry. It is divided into spaces. And every space in the middle, you can see that it is getting that vertex. You remember we talked about that dual graph. And spaces that share surfaces in this case, rather than edges in 2D, now we're talking surfaces in 3D, have an edge between them. And that creates that dual graph. And Topologic Pi, when you give it a geometry like this, it immediately converts it into a topology and immediately derives a graph out of it. So you can start asking it questions, you can start doing analysis of it. And that's the power of topologic Pi. If you are using another piece of software like Rhino, 3D Studio Max, AutoCAD, Autodesk, whatever, Revit, whatever you, any kind of product you want, and imagine yourself designing a cube, dragging in a cube and dragging in another cube, and you put them next to each other. If you don't do anything else, these two cubes will never know about each other. They'll never know that they are adjacent to each other, right? They're just sitting there. In topologic Pi, you can take it a step further and say, I'm building a cell complex. I'm building a complex of cells that are actually interrelated. So it knows. And it can, if you know that they are interrelated, you can also find the shortest distance. How do I go from this office to that office? Where is the nearest fire exit? So it starts accumulating really quickly in terms of its power. So if we have a graph that represents a building, like you can see here, there's a building and there are these red dots and black lines that are a graph. There is a branch of AI, branch of machine learning called graph machine learning. It learns not from tables of attributes, but it learns from actual graph data structures. And it can learn at the graph level, like for example, it can look at this graph and it tells me, you know, that's a duplex made out of like 2 floors, you know, identical apartments on the ground floor and on the first floor. Or if this was a hospital, it would tell me it's a hospital or a library or a prison. So that is called graph level prediction. It can also tell me, because I've seen similar buildings that have similar kind of topologies, I predict the cooling load to be whatever, 30,000, whatever it is, units. So that it is trying to predict the cooling loads or trying to predict the cost of this building. And it's trying to come up with a number that is close to the actual truth or the actual value that you know about. That is called regression, right? It's trying to find a value that is close enough, not a category, but a value that is close enough. So we have graph level classification, graph level regression. You could also have node level classification and node level regression, meaning I can take one of those red dots and say, okay, it sits between a kitchen and the door and the dining room and then some other windows. And I've seen that kind of pattern before where the thing that sits in the middle is a living room. Therefore, I'm going to predict that this is a living room. So it knows the node value. If it knows the node value, you could very quickly look up what a living room should have in it. It should have a couch, a chair, a TV, blah, blah, you know, all of that. And you can auto-complete your BIM model or your IFC model. And that becomes really powerful for missing information and trying to predict what it is and then auto-complete it parametrically. This is what I call the show-off slide. If you've seen my presentations before, I always show this slide. It basically just to let you know that topologic Pi is quite a vast library and it has been connected to a vast ecosystem of pieces of software. We have actually over the years, since 2016, been working and integrating it with all of these tools that you see here. Some of them will look very familiar to you. So you can do a lot with it. It's basically a hub of cleaning information, adding topological information, extracting semantic value out of it, and then moving on to a different platform. The roots of it is in the team that you see here, and some of these names showed up in the graph that you shared at the beginning. Professor Robert H., I give him credit because he is the first person who mentioned to me the word non-manifold topology, which is the mathematical concept which this whole thing is based on. He had worked on it, which was part of Dynamo, actually, which is that plugin for Revit. And then they took it out of Dynamo. There's a whole story behind it. But I invited him after he left Autodesk, and he was a visiting professor at UCL. I invited him to join me on this grant from the Leverhulme, and we were really fortunate enough to be given those $300,000 to develop this. Once we got that, we hired Katerina and Nicholas, our 2T8, and collaborated with Simon Lennon on topologic Pi. And Katerina and Simon still collaborate on it to this day. So the idea or the promise that we said to the Leverhulme is that BIM models are just simply, they're good for documenting and they're good maybe to give to the contractor, etc., but they don't capture design intent. they don't adhere to any kind of standard based on the software and based on the operator of the software and the standards. You get different results, and you sometimes the information is there, sometimes the information is clean, sometimes it's not. It's basically a bit of a nightmare. And this kind of lack of standardization is really hurting the industry and holding us back. So what is the alternative? How do we solve this? Because every time I show topologic pi to big firms, and we have a lot of firms that come to us and say, you know, they heard about topologic pi, they want to use it. They say, oh, we have these BIM files, we'd like to give them to you, and would you clean them for us? Assuming that somehow topologic pi is like a piece of magic. And what we try to tell them is, you're already in the kind of in a wrong position. You cannot go from complexity to simplicity. You know, it is very difficult because you need to peel away. It's much better to stay simple for as long as you can and use a reference model that then use AI and use shape grammar and use rules to actually populate your reference models with the needed information. BIM models should be derivative models, not kind of driving models. So we tried this methodology with a company in Dresden, Germany, called eProConsult. There is an amazing guy there, Ahmed Al-Tahlawi. He's from Syria originally, and he works in Germany. And he and I collaborated for a couple of years now on this. So basically, a client came to them with this U-shaped building. It's a student housing. It's a 20 million euro student housing. And Ahmed and I have been working for about 6 months on these kind of workflows. And he thought that this is a really good opportunity to show what we can do. So he went to his bosses and told them that we could analyze this building and come up with different alternatives and prove to the client that these different shapes are better in terms of daylight, better in terms of preventing isolation, social isolation, because this is student housing. You don't want somebody's room to be like in weird corner and they have to travel all around to get to the staircase and all of that, or to meet other students. So they said, fine, we will give you 3 days. And we don't have any more than 3 days to convince. So within 3 days, because we had all the workflows ready to go, he investigated really quickly, kind of what do you do if it is completely like a courtyard thing, fully, and then H shape and then L shape, very quickly. And he was able to use topologic pi to analyze the data that comes out of it. And he used kind of like space syntax type of analysis. He also used daylight analysis very quickly. And we did a bit of multi-objective optimization as well. And it proved to him and to everybody else that this H shape is actually much better. And because we had the scripts that took these simple models and converted them into Revit models, thickening the walls, putting floor slabs, putting the doors and windows and all of that, this model that you see down here is actually generated automatically from topologic pi. So rather than dealing with BIM models, we dealt with very simple test fit models. These are from a piece of software called test fit that were converted into topologic pi. And because he was able to show them Revit models, they were convinced that they can actually change their design, and they embarked on a completely new design. And now this building is actually built, and it is an H shape. So I'm proud of that. That's like one of the kind of case studies where topology pi proved its worth anyway. So as I said, we've been working with Ahmed on that. He has since used it to do categorization and kind of detection of apartments of the same type in buildings. And also Bruno Possel used it as the engine behind his software, which is called Homemaker within Blender BIM, which is an open source open BIM platform for creating IFC files. So basically he inputs topologic cubes and faces, slices the building, and it automatically creates a fully IFC compliant building with all the windows cut out and all the cornices and the doors and everything. It even has an energy model in it, all done automatically based on an analysis of the cell complex, which is in topology. this is the idea here, that this idea of complexity last not first. So if you are given, basically, this is from Kevin Crump, a colleague of mine from Australia. He was talking to me about, like, so if you have this kind of hospital wing and we want to analyze it, kind of, how can we analyze it using topologic pi? And again, the same mistake, starting with a BIM model already like complex. And what you really need to do is remove everything. You don't need any of that, and you need to rebuild adjacencies in order to find out from the nurse station how many of the patient rooms do they see. In case of an emergency, is there congestion? Kind of do congestion analysis. Where is the shortest distance to the fire exit, et cetera, et cetera. For all of these, you don't need sophisticated geometry. You need very, very simple prismatic geometry. So topologic pi has decompositional topology, meaning I can take a cube or a cell complex like this and decompose it into its cells, decompose it into its faces, decompose it into its edges or its vertices. So you can go from the cell complex to the cell, from the cell to the shell, et cetera, et cetera. I won't bore you with all of that. These are kind of like the details of it. Just know that you can kind of like decompose it. So you can ask a cell complex for its subparts. That's not very unique. Other software can do that. But what is unique is that it has compositional topology, which is the opposite, meaning I can take a single vertex in this building and ask it what or who uses you. What are you part of? Are you part of this room or that room? Are you part of this space or this wall or that wall? And this ability to ask a small part about its parents, grandparents, great-grandparents becomes really powerful. So you can kind of like climb up the hierarchy. And then, of course, there are graphs, and there are in topologic pi what we call implicit and explicit graphs, in the sense that there is graph data structures that we use behind the scenes to do our work, but there are also explicit graphs that we give to the user, and we allow them to customize them any way they want, and then they can use that for analysis. So graphs can connect to, let's say, apertures, to exterior and interior windows and doors. They can connect to exterior walls or not, or to interior topology. There are a lot of options to how you create a graph. So once you have that, you can also have lateral topology. So in this animation, I'm selecting a single cell, a single room, which is expressed as a kind of a red prism here. And I'm asking this room, who are your neighbors? Just a simple question, who are your neighbors? And it's returning a list of neighbors every time. And every time I change the room, it will give me, obviously, a different list of neighbors. If you have that, if you have a graph, you can do, and you guys are very familiar with space syntax, you can do closeness centrality, find out the shortest distance to all the other points on the graph, and then color code the face. And color coding is part of topologic pi visualization. And every time I'm cutting and kind of slicing this floor plan, I'm updating the closeness centrality. I'm rebuilding the graph and updating the closeness centrality so that you can see it. Or betweenness centrality. Basically, in this case, I took some points on the left side, some points on the right side, and I said, okay, go from the left side to the right side. Just, like almost like agents, like points. And said, just go over, and then tell me how many times has a node on the graph have been visited. And then I make it brighter. Every time it gets visited, I make it brighter, brighter, and brighter. That's kind of the concept behind betweenness centrality. So almost like the paths that get worn off in a field of grass when people are walking on them, that's what you get. So you can see literally where the bottlenecks are, here at the bottleneck, and you can see kind of there was no indication of where the corridors should be, but you can almost see that it's suggesting where the kind of main circulation arteries should be in this building, even though I didn't tell it. I gave it just a shape and a grid and just points from left to right. So you can do these types of space syntax things. You can do also a visibility graph, which is another space syntax thing. Basically, who do you see from a certain vantage point, or who sees you from a certain vantage point? And basically, you can put a few points there, and then you can also interpolate the values between them. So you can find out dangerous areas in an urban neighborhood, or visibility of a certain target, so that you can find where the water cooler is or where the conference room is. That kind of visibility graphs. We also connected it to an online platform called Victor. And this one, what you're seeing here is an animation of loading up an OBJ file and then conducting a full Open Studio Energy Plus energy analysis on it on the server, very much like what Ladybug does with the pollination cloud, but this is free. And after a few minutes, the results come back and you can see the color-coded building on the web, kind of in a 3D rotatable view. I didn't want to speed it up. I wanted you to see like how long it does take a few minutes to actually do that, but maybe we are running out of time, so I might skip this one. Well, this is the result of it. So basically, once it comes back from the energy analysis, you get either you can choose which one you want, cooling loads, heating loads, or time not comfortable, and it will color code the spaces and gives you an axis here, kind of a scale. One of the last things I want to talk about is this idea of graph machine learning. And this is also, I have to give credit to my PhD student and my co-author now. He's a good friend now and a collaborator on many papers, Abdurrahman al-Yamani. He was the first PhD student who started working with machine learning with me. And now I have other students that are starting to work with the same concept and with the graphs. But basically, a cell complex in topologic pi on the left side converted into a graph, into a dual graph with semantics. So every node knows what it is, like it's a living room, or is it a column, or is it a part of the ground? And then this data is converted into a CSV file, which gets loaded into DGL, which is a graph machine learning platform. And Abdurrahman is a landscape architect, so he was interested in the relationship between building and ground. So he was predicting the kind of relationship a building has with its ground. Is it hovering over or embedded or sitting on top of it? And we published a few papers on that. So this is an animation from his dissertation where he created a large synthetic data set, meaning that he used parametric design to create the buildings rather than grab them from real life, because it's very difficult to get data sets, obviously, in real life. So he created this parametric generator in Grasshopper, actually, and then moved it to topologic pi to create the graphs of them. And you can see the graphs in the middle. And then labeled them, or the software would label them for him, and then the graph machine learning would predict that label. This is the latest project that we are working on. This is a collaboration between myself and colleagues from the School of Mathematics. And what we wanted to do is imbue the infection risk model that they had, the mathematical model that they had, with people movement and with accurate architectural plans, not just a lot of the domains they use is just a rectangle, and they just put agents that don't move, and they tell you what the infection risk is. It's completely unrealistic. So they heard about topologic pi and they thought, can we actually use it for that? So what we did is we took topologic pi, we built what is called a navigation graph behind the scenes that allows people to move between these buildings, between these spaces, excuse me. And then we created a multi-agent system, very simple, based on a schedule. It's a very naive system based on a schedule, where we tell them at 9 o'clock you are in your room, at 10 o'clock you go to the breakfast area or to the kitchen area, 2 in the afternoon you go play cards, and we just put 6 people in there. We start now, we have a lot more models and kind of scenarios, and we just let it play out, and at every time step, we infect one person, and we, using what is called the Wells-Riley mathematical model, of dispersion, we find the aerosol concentration of the virus. And if they stay in one location for a long time, and with this high concentration of the virus, they get infected. So we calculate their infection risk. And that's what you are seeing in the lower left corner. When it goes above 0.5, there is a high likelihood of that person getting infected. And then we also used color coding in order to show what that do. This has now become a web app that is going to be used by the Welsh government and other stakeholders for decision making. And thank you, guys. Thank you for listening in. I'm happy to take any questions.
Thank you so much, Wassim, for this interesting, informative, valuable presentation. I really enjoyed it, and thank you for accepting our invitation to be with us. It's really fascinating how research ideas has been translated to something solid, which is this software, this developing ongoing software, which I will take the privilege of being the host to ask the first question, if I may, and giving time for our audience, if you would like to add questions to the chat box so we can discuss it all together. Since our community is devoted for junior researchers and fresh graduates and would like to some sort of entering this field, is not just good users. When they have an idea and something blocked them, there's no specific software to do their job and would like to invent their own software. So my first question is, for postgraduate students, how to move beyond existing architectural methods and developing their own software and methodology? What are the key steps they should take to get started? And how can they cultivate the necessary skills and mindset to innovate successful or to be successful in this field, to try to do something, not just being a good user? I don't know if it's a huge question, but I'm really interested to know how young researchers should start, how they could start to build their own software, their own ideas.
Yeah. It's a long journey, but it also requires a certain attitude. And unfortunately, the temptations are really great because there's a lot of software out there, and really interesting pieces of software that do amazingly advanced things. So the temptation is to just simply use it. And you could get quite far by being an assembler of tools. And people who are really advanced in something like Grasshopper are good assembler of tools. They find all the plugins and they put in the workflow. What they are lacking usually, and what I find is lacking, is what I call algorithmic thinking. So you have to start with the first basic concept of how do I look at a problem and express it as a series of steps, not use your intuition. Forget your intuition for a second. We shouldn't completely, but forget that and try to systematically and objectively analyze it and say, what kind of steps do I need to solve that problem? And once you have solved it once you have divided it into these steps, find out what are the algorithmic procedures for every step in order to solve it. You have to kind of enter that mode of thinking. That's called algorithmic thinking. The other thing is to think also for what I call first concepts or basic concepts. Basically, problems usually arrive to you already complex and mature, and they have been maybe even communicated to you by many people who have taken their own views of it. What you really need to do is peel all that away and say, what is this problem actually about? Not what it is, how it is presented to me by my colleague who came to me saying, oh, you know what, our BIM models are lacking this and that, and we need a plugin to kind of extract that information to be able to do the facade. This is their panic. What you really need to say is, okay, what is it that exactly I want to solve? So it's a facade problem. It is a facade segmentation problem. It's a geometric problem. It's a topological problem. And then you can start understanding it and understanding what kind of tools you want to use. There is no shortcut except ChatGPT these days, unfortunately, which is quite useful and quite dangerous. I love ChatGPT, but also I use it because I know how to program, so I know what I need out of it, and I can really bend it to my kind of will. If you do not know what you are doing, it, like everything else, it drives you rather than you driving it. So just make sure you are holding the reins and you are driving it. But it can be a very, very powerful assistant answering questions for you and helping you at least finding the area. But what I wanted to say is that there is no escape from doing the hard work of learning a programming language the same way you would learn a foreign language. You learn French, Latin, Italian, German, you learn Python, you learn C++, you learn C#. You got to learn a language. in my case, because of my age, I'm gonna now kind of date myself. I started with Fortran, moved to Prolog. We did a little bit of AI actually in Prolog back in the 90s, moved to C and Objective-C when I bought my next computer, and then moved over to web objects when I started doing web apps, and then moved over to Python at the very end, with some kind of more exotic things in the middle. It doesn't matter which language, because what I learned at Michigan, and I credit my professors, because what they did is they had 2 tracks of modules or courses. One was how to use the software that they have invented, and another module is actually how to write that software that they invented. They showed us how to write it. So we are using it, and then we are also writing it and adding to it. So I learned how to become a tool builder. And when I promote my MSc in computational methods and architecture, the tagline is that we are training tool builders, not tool users. We teach you how to build tools. And those tools might be primitive. They might be much less powerful than a plugin you find on Grasshopper, but that's not the point. The point is that you built it yourself, and it does exactly what you want. You don't care for it to be robust or all the bells and whistles. It does what you want it to do, and so no other tool can do it. But that's absolutely fine. Very much like learning how to paint, you might start by imitation. You take something you see somewhere, like some kind of small plugin, and you say, let me try to do it myself. Let me see if I can segment this plot into parcels and do setbacks and build something on it, like, because I've seen something like that in Grasshopper. Once you kind of experimented with that, you can move on to more interesting, more advanced things. It takes a long time. I've been at it for 30 years now, and I'm still an amateur programmer, really. Like I'm not a professional software developer. If you look at my code, it's inefficient, it's slow at times, but I don't care. It's not about whether it's fast or whether it's ready for commercial exploitation. It does solve a problem that I couldn't solve it any other way. Sorry, it was a long spiel,
No,
but
that's brilliant.
it's a topic that I am very passionate about, because
That's brilliant.
I try to do that.
We would like to pass these expertise to our the researchers and whoever would like to start with. And that's why we'll keep saying to our students, please start from the undergraduate, don't wait to be graduate in order to gain more skills dealing with.
You need the time. Absolutely, you need the time. So start early and fail early and do it again and again and again. Definitely.
I have a minor question, and then let's move to the audience questions. In the topological pi, are you using only topological aspects, or you are introducing also distances? Because, as you know, this debate started from 2005 in semantics. Before that, they were just using topological analysis. After Carlo Ratti's point of view about we should introduce some sort of a metric distance, and then that's why you're using metric radii. I don't know if this question is out of context, but I'm just curious about if it could be already introduced, or could be introduced.
It's already in there. You could do your analysis either topologically, meaning just number of connections or number of steps, or you can use edge weights, or you can use edge length, and it is fully 3-dimensional. So it is like, it does the whole thing,
There's an interesting question from Hendawi. He's lying, the graph approach and building like a structured data for the building is really great. Are there any potential for injection or injecting any LLMs like ChatGPT or Llama 3 or Llama 3.5 right now to respond to critical questions about the building? So you can just chat with the...
Yes, everybody wants to chat with the building and say, is this, what is below this living room, or, or do you match the building regulations? The answer is, Hendawi, is like, stay tuned. Yes, there is, and I'm very interested in this. Obviously, everybody is interested in this. There are people who are actually working on it. This is a field that is called RAG, Resource Augmented Generation, I believe. So basically, RAG is going to use the graph, hopefully those become knowledge graphs, to answer questions. And there have been already a few researchers who have done it, and we are going to hopefully try to catch up and use it. There is a paper in Cyprus at the EKD conference from Angelo Masafra, who's starting to use RAG and starting to use LLMs as well. So yeah, stay tuned. I think by next year, you're going to see a lot of that.
Yes, we are waiting for it. It might be easy.
Not from me necessarily, but you're going to see a lot of people using graphs to augment generation, especially in the area of conformance with building regulations. I've seen that a lot.
There's another question from Hendawi. He's asking nice questions, by the way. Are there any kind of bridging between Revit model and building a simple graph using topology pi, or I should start it from the beginning at the topology pi, meaning like starting from Revit, moving things to the topology pi, or the vice versa, or how?
I mean, obviously, if you've heard the lecture, I promote vice versa. I promote the starting in topology pi and moving to Revit. But if you have Revit models, you need to get their spaces, get center lines, and build simple geometries that are touching or adjacent so that you can move. I see here a question: can we see topology pi as an add-in inside Revit soon? That people have already kind of done that in two ways. One way is to use PyRevit, and it's a bit maybe complex. I haven't used PyRevit myself because PyRevit is Python and topology pi is Python 3, but it can work, and Angelo Masafra has done that. But also there is Rhino inside Revit, and you can run topology pi inside Rhino, especially Rhino 8, as a custom Python library. So you can do it if you would like to. But there isn't a product. I haven't done a plugin. Here it is, use it. No, you gotta build it yourself.
There's another question I would like to understand more about the size of the space itself. Is it limited to architectural size spaces, or it could go beyond this into an urban space? Or, I mean, having a lot of nodes, I mean, a lot of, I'm not saying complexity, but more relationships between just not adjacency, it's just more than this.
I mean, we have stress tested it to a certain extent. It will get slower, definitely, like everything else. There is nothing about topologic pi that is architectural per se. It can be applied to urban, or when we've used it with QGIS a little bit. And we've tested it tens of thousands of cells, but not hundreds of thousands, not millions of cells. I believe that at a certain point it will, because it's Python-based, it will need to be refactored maybe into more C++, or maybe more parallel processing. We have introduced a bit of parallel processing to try to speed up some of the node-to-node adjacencies, the queries in order to speed them up. We've done some good work with that. It could always use more optimization, definitely.
Well, I would like to be with you the whole day. It's really interesting and really a privilege to know you and thank you very much for accepting our invitation. And it's really an honor for us to have you with us. So we hope that we might have a future collaboration, and we hope that our audience might just contact you for further issues if they are interested. And actually, I hope that our young researchers being interested to develop their own ideas and their own tools as well. I don't know if there is a question from Muhammad Mahdi. He's asking about exporting the Revit model, technical issue related to exporting things from Revit.
Yes, yeah, we have basically, just to answer very quickly, yes, so basically you do in Revit your rooms, you use center lines so that they are touching, and you export that, any kind of format, OBJ, whatever would work, bring it into topology pi, you build a cell complex. That's when you can get an energy model for design analysis, because you mentioned design builder. You can get a graph for kind of space syntax type of analysis. The answer is yes, you can, but you need to get the mass model out of Revit.
Can GIS be integrated to this model? I'm sorry.
That's okay. It's okay. We have worked with GIS. I cannot say it's extensive work, but we have been working with Blender to bring QGIS, I believe. And the idea there was to find out, like, if two buildings are neighbors, we go building to parcel, parcel to other parcel to the building, and therefore we can build that kind of relationship. Or building to parcel, parcel to road, road to parcel, parcel to building, across the road, kind of neighbors across the road. So you can kind of start building those types of relationships. GIS in general is like a hero to us because they are very much all about topology. And they have very advanced ideas about topology in GIS. So try it. I think you could find some resonance there.
Thank you very much, and I really appreciate your time, and thank you for being with us, and thanks for the audience for being with us from the beginning. And by the way, our special audience, they are registered particularly to this. It's not open invitation. It was just if anyone interested, and we have seen that the people are interested in nice questions from their side. Thank you very much, and we hope to see you in other events and to see the audience as well. Thank
Fantastic.
you.
Thank you so much. Thank you for inviting me, and I wish you all the best with your initiatives. It's been really great. Thank you, guys.